Cool. Appreciate the introduction, Jason, and thanks for having me. Really excited to be here today, and thank you all for your time. Yeah, I think caught a bug last night, and I just didn't want to get anyone sick, so doing this virtually. Anyways, today for the talk, I'm going to talk about from words to actions, and I may go through it relatively quickly, but the hope is that we can turn it into a discussion of sorts, or if people have questions, feel free to raise hands or things like that. So today, excited to talk about when I think about the future, I'm excited for one where robots are around us, helping us with everyday tasks. And part of that requires building systems that are capable of being out there in the physical world and adapting to unstructured spaces. And what particularly excites me the most is if all of these robots were driven by the same generalist system. So for me, robotics is very much an excuse to try and build generally intelligent machines with the hope that we can build these decision-making agents that interact with the world and improve themselves over time. And I think that robotics is a fantastic place to study this because it really exposes us to all the right sorts of problems. For example, there's multimodality, data efficiency, inference speed, as well as I saw a comment just now, can't hear. Is that still the case, or?
I think maybe it's an issue on your end. Everyone else seems to be able to.
Okay, all right. Yeah. Just going onward. So I think that there's an opportunity to really surface all of the hard problems, particularly involving closed-loop decision-making and reasoning. And all of these things don't really pop up in other fields as much as they do in robotics. So I feel like it's really an opportunity to study these problems as a first-class citizen. So I work a lot on manipulation, getting robots to pick stuff up, put them down, push them around, toss them. And my team and I, we enjoy doing this with machine learning, taking data-driven approaches where we can map from raw sensory inputs to action outputs. So one of my favorite examples is on the top right here with implicit BC, where we're trying to get the robot to essentially do these pushing tasks. And I still remember in grad school, getting a robot to accurately push an object across the surface of the table was such a challenging problem because, like, as you're pushing the object, as simple as it sounds, as your end effector is pushing the object, if it slips just a little bit to the left, then your end effector has to use closed loop feedback to kind of react to that and adjust the trajectory so that it pushes the object and maintains its orientation. So it's like these subtle details, they compound on each other because of the physics of the way that friction coefficients of the objects themselves react on the surface of the table. So if you're going to try to solve this with math, it's just not really going to work. And so when we got these initial results with implicit behavior cloning, just training deep end-to-end models from pixels to end effector action offsets, it was absolutely incredible to me that we're even capable of doing these like complex combinatorial sorting tasks just from image in and actions out. So I think like closed loop vision-based policies, I'm super excited about that stuff. And I think part of the hope is that if we take a data-driven approach, then if we have a robot interact with many different things in the world, then over time, if we pool all of this knowledge into the same model, then at some point we can get our robots to interact with the physical world to learn some shared notion of bottom-up common sense or how the world works. So I think that for a period of time, we were very much interested in how we can build these shared priors. And part of that was starting up, of course, an ARM farm. This is one that we started in 2021. And the goal was to get robots to do these complex manipulation tasks involving folding T-shirts and scooping particles and various different things that required a decent amount of contact-rich manipulation. And the hope is that if we collect enough diverse data over a number of tasks, then ideally the number of cumulative data that we acquire over time, that starts to asymptote in the sense that in order to get good performance on new tasks, we will require less and less data because the shared priors of the models themselves are starting to take over. The idea was that this would be the asymptotic effects that we would see in terms of using the modes of generalization of the understanding of the physics of the world as a way to drive improvement into new tasks. So ultimately, new tasks will require less data. But the reality of the situation was that for us, this curve was much more linear than we had expected. It's much steeper. And part of this is that there's just so much complexity baked into the environment, into the object sets that you have, or the embodiment, the robot hardware, the action spaces, as well as the contact dynamics you experience during the course of the task. So I think that while I still think that this curve is bound to exist, I think that it's still logarithmic in the long run. I do think that it's much farther out than we expected, and we do need to collect a whole lot more data to really begin to see this curve happen. So another thing that we observed over time in training deep models is, at the end of the day, machine learning really is just a box. It's very good at modeling the data points inside the box, but not very good outside. So you could, and I can't tell you how many times we've created this sort of plot where if you take your testing cases and you plot the ones that perform well, they oftentimes lie within the convex hull of your training data. And the ones that don't perform well, those can be considered as cases of extrapolation. Those are outside of that convex hull. And I think that, of course, there are different ways in which you can improve the performance on cases of extrapolation. So you can certainly improve your algorithms in some way, or you can add in a prior that you know of how the world works or the situation that you're in as a way to improve extrapolation. But I think that that goes to an extent, it works until just you have to handle all of this sort of edge cases that happen. And what's interesting is that in NLP, they've found, they discovered that if you take your entire universe and put it inside the box, then every extrapolation problem becomes an interpolation one. And this has manifested itself the most in terms of large language models trained on internet text data. And these models are absolutely insane. And of course, I'm sure that most folks here have played around with ChatGPT, but yeah, these models are pre-trained on things like news, recipes, and code. And on the other side, books, articles, and dialogue. And you could compose various different things together on different parts from the internet that is learned from. So just an example, like if you go into your favorite OpenAI API and you type in instructions, steps to brush teeth with peanut butter in the style of Shakespeare, then you get a full-blown step-by-step plan. Take a spoonful of peanut butter and spread it o'er thy toothbrush. And then it ends there with smile wide and admire thy pearly whites. It's already more creative than I am. And I think seeing these models do what they do makes me question the meaning of creativity as well. So anyways, it's absolutely amazing to see what these language models are capable of these days. And as a quick primer on how these models work, the two most important things to pay attention to are the tokenization and transformers, so inputs and outputs in models. On the tokenization side, traditionally in NLP, some of the best performing models do tokenize based on per word. So essentially, every word maps to an embedding space that is also learned through gradients. But what has worked quite well has been byte pair encodings, where you take your individual characters and you cluster them based on frequency of how often they occur next to each other, and use those to essentially do a type of k-means, a frequency type clustering to basically build your token vocabulary. The advantage here is strictly computational. So it just means that with 4 tokens, you can now express more. Whereas previously you need 6 tokens to express the full set of words here. And I think one specific thing too is that the best performing language models still are based on per word. It's just that for the sake of being able to scale up, per token oftentimes has some advantages in terms of spending more model weights on the actual inner layers of the self-attention of the transformer, as opposed to trying to capture rich embeddings for every single word based on occurrences. It's also one of those things where if you have an individual token per word for every single embedding here, for every variant of bigger, then there's also not necessarily a shared piece of information that is passing on to the different variants of the same word. The other side of things is the transformers architecture, and I'm sure that many folks here are also aware of the architecture itself, and there are lots of tutorials online. But the one thing that I wanted to share with everyone here is the beautiful piece of architecture that is self-attention. So what's happening here is that when you're computing a feature transformation y, it's a weighted combination of features that are coming in from all of your other tokens, x1, x2, and x3. And the amount of contribution that x1 makes to y is weighted proportionally to the distance between x1 and y. So what makes this architecture so profound is the fact that in self-attention, the distance between x1 to y, the metric space on which this distance is computed, is independent and separate from the actual feature representation that is on the payload or is of representing the actual x1 here. So you could imagine your Q and K, your query and keys here, they work together to form that metric space from which the distance is being computed, and your V is entirely independent. It's separate, for which it's creating features for which it needs to merge into Y. So why this matters is that it contributes to the expression of self-attention. And you can actually think of previous operators that we've explored in deep learning, like convolutional operators, as a variant of self-attention, where instead of a learned metric space, you're instead basing the metric space off of spatial locality, so pixels next to each other. And each of the payloads are pixel-wise features. So this is just something to call out, which is that self-attention is incredibly powerful and expressive. And it also scales quite well. So it turns out that, yeah, if you take self-attention, have feature transformations in between, and you layer it all into a large transformers, it turns out that bigger is better. And one of my favorite examples of this comes from Noam Shazir from one of his talks in WeCNLP in 2018. And what they did is they took a language model and they trained it on all of Wikipedia except for the article on Abraham Lincoln. So that would be part of your held out test set. And the goal was to reproduce the article on Abraham Lincoln by having the language model chain together, piece together things that it's learned from the other articles, and then try to piece together what the Abraham Lincoln article might look like. So this is really a test strictly of interpolation. And of course, with a model that's of 33 million parameters, this is a smaller side. Like the predictions are absolutely bogus. This is nonsense. Abraham Lincoln was an American voodoo activist. Yeah, this is not great. But then if you get to 97 million parameters, okay, you start getting some formatting here and there, and typos go away, but still the information and the facts here are just like not true. Scale up to 320 million parameters, and you start getting formatting that kind of looks correct. The facts are still wrong, the dates are still wrong, but it's starting to look a little bit better. Scale it up to 1.1 billion parameters, and you start getting an article that kind of looks like it was written by a junior high student. And then finally, once you get to 5 billion parameters, it becomes a pretty darn good article. And keep in mind that the amount of data that's being used or fed into the language models is fixed here. We're really just increasing the number of parameters of the language model. And yeah, I think this was an incredible example to me. And for the folks that don't know Noam Shazir, he is now CEO of Character.ai, in case you've played with that too. But I think this is, they saw from an early on that scaling was the way to go for these language models. So one thing that I'm particularly interested in these days is figuring out well, we have a hypothesis, which is that somewhere within the space of language model interpolation lives to some degree robot planning, visual common sense, and robot programming. And I think that immediately, if you kind of take your favorite OpenAI playground and you type in instructions like steps for a mobile robot to fetch a Coke can from the refrigerator in the kitchen, you'll actually get a semblance of a step-by-step plan that looks pretty good. It might not be perfectly grounded to the environment that you're in, but this shows that there's some degree of sequentiality and common sense knowledge that's stored inside the models to be able to interpolate to this kind of task. So really the only thing left here to do is, for example, map each of these individual instructions, like use sensors to detect the presence of the Coke can, to an actual action that the robot can take. And when we saw this working, we were pretty excited to see that. And this is what sort of led to the work related on Socratic models and PaLM-SECAN. And there are many different ways to use foundation models, but this is one way in which we've found some pretty good working demos in terms of using language as middleware. So the general premise here is that you can have a tabletop pick and place setting, a variety of objects that are on top, And you can first take a visual language model. It can be either CLIP, AlignLit, SymBLM, Bild, MDetter. There are newer versions like SAM and others. You can try to take that and convert it into a language description of what the visual language model sees. And then conditioned on that description, have a human input, which is the task. So move all the blocks at different corners. And then you can pass it to a large language model for high-level planning. So generate a step-by-step plan, and then for each step in the plan, pass it to, for example, language condition policies. So this was one of the first instances for which we were really excited to see, oh, snap, this kind of language model driving high-level task planning seems to kind of work. And I think we were really excited about this. So this is just a live demo that was pre-recorded at some point. I used to do it live, but then I found out that I typed too slow. Move all the blocks at different corners counterclockwise. It'll generate a plan, and each of the steps of the plan are passed into Clipport, which is a language conditioned transporter nets that enables us to pick and place objects and predict heat maps for where the picking and the placing should happen, conditioned on the language description. So what you're seeing here is typing in language commands and then having it break it down into steps and then passing it to Clipport. There's like way to actually undo that last step. I've always wanted a Control-Z button on my robot, but that works simply because everything is being passed back into context through the language model. Yeah, you can also do on various tasks like, okay, now sort the remaining blocks in the same way. So a little bit of contextual reasoning there. This demo and collab is available online, so you can download it. It will spin up a PyBullet environment in your browser inside the collab instance and then ship over videos. The actual runtime of this model is pretty fast. So I think usually the runtime is just mostly bottlenecked on whether or not it can ship videos to you in time from the simulator. Cool. So with this particular approach, you'll notice that the vision language model here is only providing a language description of the state at the beginning. But of course, we also want some mode of replanning that happens. And ideally, we can have the visual language model provide feedback after every single step that we execute. So we did this with, explore this with inner monologue, where we divvied it up into scene descriptor and success detector. These are all driven by VLMs, and the scene descriptor would provide what the environment is capturing, or it captures what the environment is, and the success detector just simply evaluates if the robot did the thing. And the idea was to use the visual feedback here as a way to ask the language model to replan in case something failed. So this example here is like, can you bring me a drink from the table? Go to the table. I see Coke, water, chocolate bar. Do you want water or Coke? Coke, please. And then action was not successful. Retry, action was successful. And we tested this on a couple of environments. I think that language is quite promising, but it also has a bunch of limitations. One is that it loses spatial or numerical precision. It's also highly distributionally multimodal. There are lots of different ways to say the same thing. And that also has modeling challenges. And also, it's not as information rich as other modalities, for example, images. And a burning question for us also has been that it seems like these models appear to capture a lot of high-level common sense and intuition, and we can definitely use that for things like visual common sense or high-level planning on robots. But a key question is, how far can this help in terms of control? Are we still limited by imitation learning, reinforcement learning, or engineered policies? And I think one thing to realize is that intuition and common sense, I think, is not just a high-level thing. When it applies to low-level behaviors too. So specifically, if you were going to tell a robot to move a little bit to the left, what does a little bit mean? I think it's highly contextual. Same goes for temporal commands like move faster or functional, balance yourself. A lot of these things are very much sort of ingrained inside the way in which we expect robots to behave in the future. And I think of it as cases of behavioral common sense. I call it the dark matter of robotics because we know that it must exist, but it's very, very hard to pin down. And I think that certainly you can try to collect a massive data set of what every possible variation would potentially mean. But I also think that there's a possibility that we can extract these priors from language models because like when you're reading a book and you read a snippet that describes, oh, as you gently push your fingers against the roughness of the bark on the tree, and then like all of those subtle words that describe the feeling of how you sort of interact with the world, I think is somewhat baked into the language model. They're just not quite extracted in the way that we want to. I think that, so this leads to a project that we started exploring, which is using language models to write robot code. And specifically, these are using models that have been fine-tuned for code writing. And so you would take these models, you would fine-tune them on a lot of GitHub code, and then they would be just very well positioned to write Python code, for example. And just as a very simple example of this, hopefully y'all can see my screen. If we say something like, if you see an orange move backwards, then we can like define some code here. If detect object orange, robot.set velocity x equals to negative 0.1, y equals to 0, z equals to 0. And we're going to give it a new command. We're just going to say move left until you see the apple. So for why we're doing this and passing this to a language model is that we just want to give it a couple examples of the kinds of APIs that we have access to. So here it's the detect object function and maybe like a set velocity function prescribing a particular canonical coordinate frame. So we're framing the language to code commands. And if we just run this, the language model will predict this following snippet of code here. There's a couple subtle things to notice here. One is that, first of all, it's changing the object from orange to apple, but then it's also switching out the if statement to a while not statement, which is kind of cool. And it's also assigning a canonical coordinate frame. So here, x negatives, for example, it's assigning that left and right would probably be the y-axis here. And I think this is really interesting because these are all like subtle things that we expect our robots to have one day autonomously. And some of this reasoning appears to emerge from large language models trained on code. And we can also go on and do something like do it again, but faster to the right and with a banana. So while not detect object banana, set velocity. So here it's flipped the axis here and also increased it by a little bit, which is neat because like, again, to the point of saying something like move it a little bit to the faster. If you actually wanted to train a system to do that end to end, you got to collect a lot of data of what faster means. But then here we just get it for free, which is great. We could also do tell me why you stopped moving. So a little bit of HRI here. And it's going to give you a print statement. I stopped moving because I detected a banana. So I think what's really exciting to me about this is that we can use these models as sort of expanding the expression of the planning that we used to do, but to the full expression of code. And so you can really leverage logic structures like the if statements and the while statements. You can even use third-party libraries to kind of do very complex tasks as well. And this was a project that Jackie had led here where pass in the language instruction, and then you have the language model produce code. And if it happens to define a function that is undefined, then it could go ahead and redefine that function on the fly. And so you basically have this hierarchically, dynamically expanding code base that writes itself over time. What it does is it would be chaining together existing perception and control APIs so that it can progressively do more complex things. And I think this harkens back to some classic work in robot programming. So infinite use of finite means, using compositional modularity as a way to generalize to new instances or new cases. And I think that this is something that is I'm excited about in terms of revisiting because yeah, and I'll talk a little bit about that down in a couple slides. Another thing that Jackie had shown here was that this process of recursively defining undefined functions also becomes really useful for standard NLP benchmarks. So we also improve performance on human eval by quite a bit for coding benchmarks. So part of why this all works is driven by in-context learning, which is a version of supervised meta learning. So you'll notice here back in this example, we formatted our task input and code output as pairwise sort of examples that we're passing into the model so that it knows what to work off of. There's two reasons for why this works particularly well. The first one is that normally when we write GitHub code, we're oftentimes expressing what our next snippet of code would be doing in the comments section. So this is kind of like siphoning the language to actions type framework within the same kind of distribution that we would be seeing on GitHub code. The second thing is that in-context training is essentially packing in multiple examples of the same task from the same data set and using that as a way to generalize to new distributions. So one thing that I want to call out, and I think that is a little bit of a misnomer recently, is that in-context learning is not emergent. It is something that you have to explicitly train for. So when you train these language models, you need to pass in into autoregressive models where you pack in multiple X, Y examples. In NLP, a translation task would be, this is from French to English, maison, house, chat, cat, chien. The idea is that the language model will learn from your distribution of input-output examples here and try to complete the task by simply predicting what comes next. So there's a little bit of history behind why this approach ended up occurring or developing the way it did, because previously in NLP, to get good multitask performance, you needed a condition on like a special token that described the text. But in the end, what ended up happening, or what ended up working better, was if instead of directly passing in a special token to describe like a task token, you would instead replace that task token with actual input-output examples pulled from that distribution, then that actually works better, albeit at the cost of more compute. So here, more formally, it's just x to y, x, y, and then x query given y query, predict y query. And your function f is drawn IID from a distribution of f that you're trying to capture. One specific thing here too is that there have been prior work that are trying to study the modes of generalization for in-context training, and various different works also show that if you try to use MLPs to try to get this kind of generalization, it's a little bit more linear, but at certain point with transformers, they can generalize to unseen f that fall within the same distribution of functions f that you would capture during training. So at some point, so this is from a paper from Kirsch et al. For general purpose and context learning by meta-learning transformers. Also, it appears that if your training distribution is Zipfian, then the emergence of in-context learning, which is a very special case of in-context learning, that tends to work better with transformers than other model architectures like Manila RNN and LSTMs. I also want to call out specifically that while this is a recipe that works for NLP, I think it is still very much open-ended for whether or not it helps with robotics. And specifically in NLP, say that you have a captioning data set. The problem is that in NLP benchmarks, the way we evaluate success is based on like BLEU score, which is just a bag of words type computation, which means that if you have an algorithm that generates short captions for a data set full of short captions, and it generates long captions for a data set with long captions, then that maximizes performance. But then oftentimes when you train models with multitask learning, then and you mix all the data together, then oftentimes you'll be predicting long captions when you're supposed to be predicting short captions. So the reason why this even gets good numbers on NLP benchmarks is very much because of the fact that from the input examples itself, you can pick out how long the captions should be roughly, because they're being pulled from the same task distribution. And then you can predict a new caption that is roughly of the same distribution as your input-output examples. So it's a very kind of nuanced reason for why these models perform so well in language. And I think just wanted to put that out there. There's a lot of asterisks behind why that works. Okay, so back to language models that write code. Jackie here has done amazing experiments here to show that you can even do things like use NumPy and SciPy code to like draw the convex hole around something and get a robot to do something with respect to that. You can even get a robot to draw shapes. I think like this here was an example bottom right of like getting the robot to draw two pyramids on the ground underneath the sun. It's just like insane to me that we can get these robots to do these kind of things now, which is really cool. And most of these, nearly all of these capabilities are zero shot. I think some of them have some proximal examples that are close in context, but other than that, much of this is like capabilities that we can just get off the shelf. Your language models have read your textbooks too. So they are pretty good at, when you prompt them in the right way, you can get them to fetch things like PD controllers and impedance controllers and write out the math in Python, which is pretty cool. You can also get multilingual support, of course. So you can type in Chinese or speak to the robot with emojis, and it'll still do the thing. And I think what's also really interesting, at least for me, is when we think about building the foundation model for robotics, it's got to be something that is potentially cross-embodied, meaning that it should support multiple action spaces. And what's kind of cool is that when we express things in code, there's an opportunity in the sense that the action space, as long as we have a code-like representation for it, then you can get some decent amount of generality from that. So here, this is an example where we prompt the model with, oh, look, I'm an omnidirectional robot, and my available actions are move up, move right, and move back. And now the command is to make a U shape 5 meters wide and 10 meters long. And then the robot sequences the commands that would do the thing respectively. So now if you prompt the model, I am now a unidirectional robot with available actions only turn left and move forward, then the way in which the robot needs to generate code is slightly different, but it's kind of cool that it can still make use of the APIs in the way that we expect it to. So I think this is pretty surprising. So I think there are a couple extensions to code as policies. I'm going to briefly call that as well. I think if you, for example, were reconstructing a 3D scene and you had like a 3D voxel grid or a height map representation of your map, what you can do is fuse visual language features into that map. So like clip features, for example, and that allows you to generate heat maps of target locations that you want to be. So what's kind of cool is that if you pair it together with code as policies, then if you make the query to the map as an API call, then what you can do are navigation tasks like, for example, bring me in between the sofa and the chair. And then it'll compute a heat map of the sofa, heat map of the chair, and then compute the distance in between using some NumPy. So I think that was like previous language to actions type tasks that I think before this project, it was kind of unclear how to exactly tackle. So there's a fair bit of spatial reasoning. Move a little bit to the right of the kitchen counter. We can also use language to code for cost and reward functions. So if you wanted to do optimized control trajectories with MPC or RL, you can do that. And we're really excited about this because it kind of divvies up the reasoning where the language is more responsible for the high-level parsing of objectives, and the low-level part is really doing what robotics does best, including optimization. So there's like fun videos of the robot doing twirls and doing a handstand and doing a moonwalk in simulation. So I think it's pretty exciting. Here are some examples of like more dexterous manipulation, or this is not really dexterous, but some manipulation tasks, which is like, can you put the yellow fruit in the bowl? I'd like the apple there too. And as long as you have some version of reward code that is within distribution of the things that you can prompt a language model to produce, then it can do the tasks here. So here, and the banana to the other side. Okay, I'll put the banana in the right corner. And then the place is a mess. Can you tidy it up? Tidy it up, and then it'll put the fruit back into the bowl. So it's like generating these trajectories to MJPC, with just the simplest predictive control. And then, yeah. Actually just empty the bowl. Okay, I'll flip it. So I think that's pretty cool. Okay, so zooming a little bit back out, I think that in terms of scaling robotics with foundation models are in a spot where there's just lots of internet data, the existing ones that we have today at least. And in robot learning, we're just in a position where we don't have a lot of robot data. And it's a bit of a chicken and the egg problem because we need a lot of robots out there doing useful things first before we can actually collect all the data for it. Of course, you can build an arm farm, and in this arm farm, you can collect 50 expert demonstrations, and now you can do some pick and place tasks, 500, and you can do some more combinatorial complexity tasks, and you can also maybe scale up to 5,000, and now you can do some more complex, granular, like contact-rich type tasks, like scooping up particles. But I think it's one of those things where you got to keep thinking to yourself, it's like, in order to, once you linearly increase in the complexity of the tasks, is it the case that the amount of data that we need to collect to capture that complexity, does it grow exponentially? And does this persist? And so I think if we think a little bit back about how much data is being used to train foundation models, for PaLM, which is our language model, total data set size there is about 780 billion tokens. And if you do a little bit of napkin math, supposedly where you have 256,000 token vocabulary, where every token has an embedding dimension of 18,000. So these are pretty expressive tokens. If you had robots producing actions and each action was a token and you were producing this at 30 hertz-ish, if you scale it up, then napkin math basically tells you that in order to collect a palm-sized robot data set, you need about 100 robots for 24 years collecting mostly diverse data. So that's quite a bridge to gap, and quite a gap to bridge. And I think that part of the way in which we could potentially meet in the middle is by trying to find other sources of data, and this could be simulation or YouTube, or potentially improving the data efficiency of these models with prior knowledge. Those are certainly valid approaches. But I think one way in which we can help close this gap is really embracing foundation models for what they are today. And I think of this entire plan of being able to bring robots out into the world is very much in phases. And I think perhaps in the first phase, where we build with off-the-shelf models, this would be great with less than 100 robots out there in the world. Once we increase the number of robots that we have from 100 to 1,000, then the amount of data that you can collect roughly starts to become on the order of which you can fine-tune off-the-shelf models. And then once we get to 1,000 plus robots over 2 years, then that gives us potentially enough data to train our own models. And you might be asking, like, building with off-the-shelf models with things like code as policies, isn't that like essentially doing modular type approaches, something that robotics has done for the past 30 years? And I would say that yes, but also some things have changed. So specifically, back then, if you had all of these modules and you wanted to piece them together, back then you needed a robotics expert to piece all the modules together. So there was still a human in the loop. But now we can replace the human here with language models that can help us compose these things together autonomously. So I think we do have an opportunity here to make robots useful autonomously outside just by training these foundation models together. So in terms of phase 2 type approaches, at least at Google, we've been saving all of our data that we've accumulated over the years, and that kind of gives us we can poke at some questions related to fine-tuning off-the-shelf models. And one of the recent work we did was PaLM-E, an embodied multimodal language model. So this was taking a large language model and a vision language model, and then putting them together, and then everything is differentiable, so everything is end-to-end trained. And we fine-tune that on the robot data that we have. So here, the architecture is fairly simple. You could imagine you have your classic language model in the middle, and text tokens are going in, and this is like the orange blobs here. And we're also predicting, for example, step-by-step plans. But the difference is that in addition to text tokens, we're also passing in images into encoders that would then give us continuous embeddings that we can pass in. So you can think of these as continuous tokens that represent images. And the large language model would be fine-tuned to process these things. And the actual embeddings themselves are not fixed. They're constantly being adjusted by gradients because this is trained end-to-end. You can also feed in like state neural embeddings that are coming in from like your favorite scene neural representation as well. And how this project actually started was just from a really simple observation, where if you wanted the robot to do step-by-step planning and you had this simple case where you had like a yellow block on top of a blue block and you asked it to grasp the blue block, without seeing the image, the robot or the language model might just tell you, okay, grasp the blue block, but then there's an object on top of it. So this is a simple example, but it just shows that a lot of information and constraints about the world that you're working off of can exist inside of the image itself. And by being able to give a model access to that information is what allows it to plan better. So I think that we're really excited about what we can do with this kind of image conditioned language model. So also some findings that I think would be useful for this crowd. And I also want to put an asterisk on the results here because we were also a little bit strapped on compute. We had a limited compute budget for only 10 days. And so in order to get results sooner than later, we have higher learning rates and smaller batch sizes. So take that with a grain of salt. We didn't do like the full hyperparameter sweep that we hoped. But the two observations that we've seen that seem to be interesting is, first of all, fine-tuning pre-trained models helps. So if you had your robot domain and you had used pre-trained models from VQA data sets, then fine-tuning on top of those would yield better downstream performance. And this applies in various different other domains as well, as people have shown. So I think this is a very promising to see that it works for larger models too. And larger models, they also retain pre-trained performance. So there's a lot of, there's an area that's really focused around catastrophic forgetting and how you can prevent that. And what we found with Palmi was that you can continually track the language model performance. So this is just natural language tasks. And we're not fine-tuning on those tasks. We're just fine-tuning on vision language tasks or robotics tasks. And what we find is that if you fine-tune on robotics data, your language performance drops significantly when you have a smaller model, 12B. When you start to increase the size of the models and the parameter count, that performance drops starts to become smaller and smaller. At some point, it just becomes negligible. And I think this is just in part because larger models, they appear to have more weights to store information, but then also be able to take new patterns that it's seeing and then fit it into the existing patterns it's seen before. So I think it's, yeah, particularly interesting to see this kind of scaling happen. There's a couple more recent threads as well, which is and happy to chat about this more offline, but we can also model the uncertainty of language models using some work from conformal prediction, and we can characterize the uncertainty with some statistical guarantees as well. So that allows your robot to basically, if it doesn't understand something, it can ask a question. And also there's some interesting threads related around language models as general pattern completion machines. So because of the nature of the self-attention mechanism, there are some natural symmetries that are being exploited. And this allows some degree of pattern extrapolation in ways that we might not have expected. So I think some of the really cool demos that we've played around with are like things like having a language model prompted with just a bunch of numbers, be able to discover a self-balancing car pole controller, which is kind of cool. Well, that was what I had. That's it. If there are any questions, happy to take them.
All right, yeah. So I think now we have about 10 minutes for Q&A with Andy. So if you have questions here, just shout it out. And for folks on Zoom, also feel free to unmute and just ask your question. Yeah, Frank, you want to go ahead?
Yeah, I was curious about kind of mid-level instructions. A lot of these ARM robots are going to be using very low-level instructions. So thinking more of like kind of the module level or mid-level or something, say, like I'm working on NPCs in games. So curious if you have any insights there, especially around fine-tuning.
Yeah, I think it's the one example that comes to mind in terms of.
So let me give you one.
Yeah.
Sorry, just one clear example would be like if you have a lot of these, if you have a lot of low-level instructions, there may be only like a handful. But if you have a lot of modular ones, that are composites of those, there might be hundreds. So giving them all to a prompt, for instance, having to detail what they are, what the parameters are. Curious if you've looked at that level of things. Thank you.
Yeah, I think it's a great point. I think in terms of like different levels of hierarchies of reasoning, certainly like the more higher level you are in that hierarchy, the broader the scope of things that you can capture. And certainly, I think that when you mentioned mid-level instructions or representations, I wasn't exactly sure the example that extends, but then I think one that maybe I've been thinking about a lot recently is like if your robot was a tennis playing robot and you had an instruction that said, you made a C shape in that swing, but you want to make that C shape a little bit broader or bigger. There's like a lot of common sense that goes into that. That's like not only low level, but also a little bit high level too, because it's like you have to picture what a C shape looks like, map that to your embodiment, construct a trajectory, and make it a little bit bigger. Like all of that requires a substantial amount of, I think, mid-level reasoning that I don't know exactly what is the right way to capture. So I think it's certainly an open-ended question. And if you're working on NPC in games, for example, there's lots of instances of that, but maybe showing up in different forms. And I think that's really exciting to explore. Considering actions characters and sims can do so much diversity. Yeah.
Thanks for the great talk. So I was wondering, do you also have like anything thought about like common sense related to the shape? Like maybe the action is same, like pick up a box, but the shape is different. Like picking up a can versus picking up a plastic bottle or a glass bottle, or picking up a ball, picking up a cake. Like all these are same actions, but they have a different way of approaching because of the shape, form, and physical. And maybe LLM can give you information about like what these things are and how soft, hard, and materialistic property or all those aspects. So what's your thought on that?
Yeah, it's a very good question, and I think that geometry is certainly one of those things that our language models really struggle to reason at. If we were going to say that, the left corner of that object is actually really sharp and it's protruding about 3 centimeters upwards, and I don't know, it's made of like metal or something. Like all of that information, it's pretty challenging to get language models out of the box to reason around it. So part of what I think is particularly excited about is if we're able to, there are different ways to approach it, certainly. One of the ways in which PaLM-E tries to poke at that question is passing in the continuous embedding from the neural scene representation, with the idea that if you had a 3D representation where the information about geometry and shape was kind of encapsulated inside the token itself, then you're basically teaching the language model to speak shapes. And I think that there's an opportunity there to see how far we can push that. Although in this framework, we are only producing actions. So I think that if there's a way in which you're also producing something that's related to the continuous embeddings, it could be cool.
Thank you. And also maybe the LLM can provide a bit detail on the shape also, because it know how an apple look and a banana look.
Yeah, absolutely. I think if you like spatially zoom in into a problem, maybe like it becomes like you can basically formulate a hard, challenging, dexterous, low-level manipulation problem as a high-level one, because you've effectively zoomed in the context so that the planning around the subtle manipulations is mapped onto something that the language model knows how to do. So that's cool.
Great talk.
Okay,
I think that's a
Theo,
question.
I have a question. You want to go ahead?
Language models suggest adding and giving context for robot instructions or for more low-level robot actions. And I'm also wondering what current limits they can probably or can.
Fiona, I have trouble hearing you. I don't know if it's just me. I think it's like every other word drops out.
Yeah, Fiona, do you want to type your question? And maybe we can get back to your question and we can put another question in the meantime.
Oh, okay, yeah, I can type it.
All right, yeah, so before that, Andy, yeah, I have a question for you. So
Yeah.
I'm curious to hear your thoughts on how can foundation models help learning like complex, like long horizon skills or skills or tasks that require high precision. Like as an example, like pre-verbal infants, like infants, 1 year old, they can't speak, they don't have any language capability, but they're much more dexterous and capable than our best robots today. So to some extent, learning language manipulation seems to be able to be independent of language acquisition. So for those tasks, do you see these language-based foundation models to be helpful, or do you see that we need a different path towards solving those tasks?
Yeah, I think the short answer to that question is I think we need a different path. But I think we can be inspired by work that is happening in multimodal models. So specifically, I think that what we've done so far with language models is kind of like basically framing a long horizon prediction problem as a short horizon prediction one, which has its limits because then the semantics of every step that we've broken down into is relatively high level and doesn't capture the low level things to sufficient detail. And I think that language, because it's so highly semantic by nature, I think that it's going to be challenging to really sort of model the intricacies of precise manipulations and how objects, when they collide with each other, they slide and then maybe like react off of each other due to contact dynamics. And I think the one thing that I think could really help out with that is another foundation model that is starting to work, which is video prediction models. And I think just 2 years ago, we had an intern working with us and we were trying to get video prediction models to work, and they're just always not that great, like the blurry predictions, and then they just kind of like you can barely get like there's a paper Fitbit that was just barely getting the model to overfit on one video. But I think now with more compute resources as well as new ways of formulating the prediction problem into diffusion, I think that we're starting to see a lot of promising signs in terms of predicting the future or predicting future rollouts in terms of image pixels. So the way that I see a potential dynamic happen between leveraging these video prediction models is that you can have a high-level planner generate a bunch of possible next steps. And then for every step, you're passing that to a video prediction models just trying to generate a rollout of what it thinks the future might look like. And in the image representation itself, you may be able to capture in the frames the dynamics of the objects and how they react to each other. So this is kind of like taking the what we can't express in language to try to express it with images, which also, of course, has its own limitations, but the benefit of which is that we can leverage pre-trained models that have been trained on lots of YouTube data. So I think that there's a opportunity here, which is that we can ultimately build algorithms that are doing this massive tree search through both video space and language space, and then trying to like plan out and imagine a future for which it actually does the task successfully, respects visual constraints, and also potentially captures a little bit of physics information.
Thank you. Yeah. I think Fiona's questions are in the chat now. So.
Yeah. Do you see language models as being more useful for high-level planning given or giving context or for outputting low-level actions? And what limitations to PaLM-E, SeiKen are being worked on for future work? So I think language models, yeah, they're I think so far we've seen them be quite successful for high-level planning, and to the extent that they can output robot actions, I think it's quite promising to use their code writing capabilities. What limitations to and I think the one limitation for PaLM-E has been that we are still only outputting language. We're not really outputting a full multimodal distribution. So I think that some of the things we're looking at now is like focusing on also multimodal generation, because then we can do things like multimodal chain of thought or various different types of things there. I think also like the another big challenge for something like Palm E is that we're still very much funneled within the training distribution of VQA datasets. So this is like standard image in and text output. And VQA datasets, they oftentimes don't capture good spatial understanding. So if you ask Palm E things like, is the block to the left of the robot, it's only like probably 50% chance working because just random chance basically, because like these VQA data sets, they don't necessarily capture that information. I think it's mostly just at the end of the day, your capabilities that your language model or vision language model can capture is very much defined by your training data distribution. So we have to be able to expand that in ways that we expect test time performance and test time capabilities. So I think we're working a lot on that.
So just a follow-up to that, like in the Palm E work, we showed examples where when you fine-tune on downstream robot tasks, you see positive transfer, and if you fine-tune on multiple of them together, the performance will increase. Does that have anything to do with the nature of the downstream task being like similar to like visual question answering tasks, where what the language model really has to figure out is like relational concepts within the robot scene? Like, have you considered maybe fine-tuning on downstream tasks that's like that require much more spatial precision? And if you do that, do you expect to see any positive transfer?
Yeah, it's a good question. I think we haven't quite studied super precise tasks, but certainly like some signs of positive transfer on these robot tasks, I think does come in from a more semantic type reasoning. So one example is like some of the demos we show is as you're pushing in various different objects on a tabletop, you can replace some of the objects with other objects that you might not have seen before. And some of that simple object level generalization appears to work quite well. And this is just because by nature, the VQA data distribution is very much object centric. But I think once we get into really precise manipulations, some of that reasoning might start to fall apart because yeah, in terms of like, oh, subtle, like we're 3 centimeters of distance apart for these two objects. That kind of spatial reasoning, I think, is not quite within the distributions that we have. So certainly, I think that one way in which we could improve models in that aspect is by having some explicit training data, be it in terms of robot domains or even in the VQA domains themselves. If we had some amount of data that was capturing spatials, I think there will be some transfer that happens. It just needs to appear in the training data at some point. Right now, it just doesn't at all.
One last question.
Okay.
We're running a bit over time.
Oh, okay. Yeah. I think so in terms of using large language model as high-level planners, we've seen that they work quite well for tasks such as, like in Secant, where you want to clean the table, or for the tasks that you show in your prior works. I was just wondering, what do you think are the characteristics? But obviously, they do not work on like all sorts of tasks, and they still seem like not as good as humans in many scenarios. So I was wondering, what do you think are the characteristics of some tasks that they don't perform quite well on? And yeah, I just want to, I'm curious about like what you think are the limitations of at the moment as a high-level planner.
Yeah. One interesting thing about these language models is that because they're trained on a generic corpus of text, the kind of common sense knowledge that is being stored is very much influenced by the general bias of what the internet thinks makes the most sense. So I guess another way to put that is like, if you gave instructions to go fetch a Coke can from the refrigerator, it's going to assume that you have a refrigerator in the kitchen and that you want to open the door and the Coke can's there. But that might not be true, right? Maybe your refrigerator is actually somewhere else. And for whatever reason, we need to get these models to be able to customize themselves to a particular environment. So I think while these common sense pieces of information I think are useful for like making a general guess of where things are or a general guess of a plan, I think the key thing is also building systems that can adapt to the new environments that they're encountering. So this could be through feedback, for example. If a person was saying, no, actually my refrigerator was elsewhere, can we build systems that can, for the foreseeable future instances of replanning, always know that the refrigerator is now within the location that which you've put it in, maybe in the living room. So I think like as we approach real world problems, a big key thing that I think is missing from language models is the customization to preferences or customization to the particular specific domain that you're in, because that's where all the subtleties start to emerge. I think there are various different ways to potentially do this. So people have explored like having a big library of information that you're pulling from, and as you're drawing that in, providing that as context to the model. There's also other various different forms where you can fine tune the model itself to try to be able to capture some of this information. But definitely like, I think that being able to get these systems to self-improve to your new domain, I think is the big next step, in my opinion.
Thank you.
All right, let's thank our speaker again.
Appreciate it. Thanks for having me. Thank you all for your time.